If you ask me what the quadrilateral is, I can respond in about 17 different ways. That's because of how many different unique and special properties there are of quadrilaterals that we're going to learn today, starting off with the basics, which I'm sure most of you know. The area of a square with side length s is s squared, perimeter 4s, and for a rectangle, area is base times height, and perimeter is 2 base times 2 height. Now let's solve a application of this seemingly simple concept. A large square region is placed with n squared gray tiles, each measuring s inches on a side. A border d inches wide surrounds each tile. The figure below shows the case for n equal to 3. So basically, each of these sides of each of these tiles is s, and we're given that there's a border of d on each tile. So this border, all of these lengths are going to all be d, all of them, as you can see here. And I'm not going to draw them all because that's going to take way too much time, but hopefully you get the idea. All of these are borders that have length d. So this is just n equals 3 though. We're going to need to do it for n equal to 24. Let's draw a picture over here to see what we're looking at. Okay, so n equals 24. Essentially, we've got a large square region and basically we've got, it says n equals 24, so there's n squared, so 24 squared gray tiles, right? 24 by 24 essentially. So let's draw some of these in with a color. Maybe let's do blue this time. So we've got 24 of these tiles along one edge. There's 24 of them along one edge, right? And then there's 24 along the y-axis essentially. So there's like 24, there's 24 rows of 24 of these squares, and the side length of each of these squares is s. The distance between the other sides is d. So we're given that the 576 gray tiles cover 64% of the area of the large square region. Okay, so we're given that these areas cover 64%. So how do we make use of this condition? First, let's find the area of all of these tiles, of course, in terms of our variables. It's a 24 by 24 grid of, so it's going to be 24 squared of these 24 squared gray tiles. Each of these gray tiles is s by s. So you know the formula for area of a square, s squared. So 576 s squared. And also the total area of the entire region, what will that be? Well, the entire region is a square, but what is the side length of the square? So to find the side length of the square, there's a bunch of pieces. Let's look at the 3 by 3 case to get an idea. So for the 3 by 3 case, there was 3s, right? And then 3s, and then plus 4d, because there's 4 in between regions, essentially, because there's 3 tiles in a column, so 4 of these in between regions over here, which each have length d, right? And then these lengths are all s. So the total side length of the square would be 3s plus 4d, because there's 4d regions and 3 side length s regions. So the side length of the square, 3s plus 4d. This is a little bit more. We've got 24 of these. There's 24 tiles in the column, so there's 24 of these s regions, so 24s. But then we've got how many of these d regions will we have, right? Because d is the length of the border. How many of those borders will we have? Well, as we saw for the 3 case, the border is just the number of tiles in the column plus 1. So plus 25d. And the reason this is true is because each of these squares has its own border, except for the final square, which will have 2 borders, one on each end. So there's 25 of these border lengths. So overall, the side length of the big red square, 24s plus 25d. So that means the area of that square is just s squared, so, or the side length squared, which is this. And this is the shaded area, this is the total area. We're given that this ratio is 64%. So let's write that out, 576 s squared, or rather, you know what, it might just be better to write it as 24s squared, right? Because this is 24 squared times s squared, and then that's going to be divided by 24s plus 25d squared. And this is 64%, which is 64 over 100. And we can simplify this to, let's go to the other side. Whoop. Oh no. 16 over 25. Now notice that this over here is a square. Both the numerator and denominator are perfect squares. And same thing for this side. So what we're going to do is take the square root of both sides to get 24s over 24s plus 25d equals square root of 16 over 25, which is 4/5. And this gives us 120s equals 96. Now we just cross multiply, right? 120s equal to 96s plus 100d. 24s, that means that 24s equal to 100d. But we're asking for the ratio of d to s. So that means that we've got d. Let's move all this stuff up. Oops. So let's move it up so we get some more space. But we're essentially asked to find the ratio of d to s. So from here, it's not that difficult. We can just see that 24 over 100 dividing by 100 to both sides and dividing by s to both sides. We get 24 over 100. We move the 100 to the other side and move the s to the other side equals d over s. And 24 over 100 simplifies to 6 over 25. So our answer is 6 over 25. Whoops. So 6 over 25 is the answer. Let's quickly recap everything for this problem. So this problem really did not use anything more than formula for area of a square. Yet it was still so interesting. So we saw how it was essentially a 24 by 24 grid of squares with side length s. The area of all of these gray regions, I didn't draw it gray, but you can visualize it, it's gray in your mind, is 24 squared times s squared, which is just 24s squared. And the total area of the entire big square, well, to do that, we first found the side length. We found that there's 25 of these border regions because each of these squares mapped up to one border region, but the final square had two border regions, so 25 border regions plus 25d. So we got that this quantity over here equals this quantity over here. And then we took the square root of both sides to get this equation. We cross multiplied, found the ratio, and got our answer from there. Simple formula, yet it's still a cool, interesting application. Okay, now we're going to move on to rhombus. The area of a rhombus with two diagonals, half times the product of the diagonals. And the reason this is true is you can imagine drawing a nice big box around this diagonals. And look here how it's the d1 times d2. Well, this is d1, so it's the same length as over here. And this is d2, so it's the same length as over here. So this is d1, and this is d2. So the area of the rectangle, d1, d2. But notice here, each of these parts is divided into two. The two red parts have equal area. The two blue parts have equal area. The two orange parts have equal area. And the two purple parts have equal area as well. So this triangle makes up half of this region, right? This over here makes up half of the region here. This over here is half of its rectangle, and this over here is half of its rectangle. So overall, the area is half times d1 times d2 squared. And the perimeter we can do by using Pythagorean theorem. This is d1 by 2, this is d2 by 2, and then Pythagorean theorem gives us that this is d1 squared plus d2 squared by 2, and then there's 4 sides, so we end up with this formula, 2 times square root d1 plus d2 squared. Okay, parallelogram. Now parallelogram has base B and height H. Remember, height is not this length side. Area is just BH. And the reason that's true is because you can imagine drawing that here. And then notice how these two triangles, they both have the same base and the same height. So you can kind of imagine plopping this triangle, plopping that right there to form a rectangle. So BH. And now, trapezoid. The area of a trapezoid is just the average of the bases times the height. And the reason that's true is we can, again, as you can see, we're noticing a pattern here. Quadrilaterals are we're really breaking it down into triangles. So as you can see here, this is the area of this part is just B1 times H. So B1 times H. And the area of these two triangles, well, their bases, they sum to B2 minus B1. Right? And we can imagine putting these two triangles together. Take this triangle, merge them together. So that's like that. And notice because the B2 minus B1, that's the difference between these two sides. So this over here is B2 minus B1. So the area of this triangle is just B2 minus B1 times H over 2. And then we add that up to BH to get our area formula, which is the average of bases times height. And as you can see, these are simple shapes, so it's not too complicated. But as we move on to more complicated shapes, there's still a key idea of triangles that we're going to have to break it up into. Now let's try an example. Let's now solve this interesting problem that uses Pythagorean triples. In quadrilateral pair, PE equals 21, so let's mark that. EA is 20, AR is 15, RE is 25, and AP, what color should we use? Let's use blue. AP, not AP exams, but this is going to be 29. Okay, and we're asked to find the area of this quadrilateral. Okay, so first thing you might immediately notice, for now, actually, what I'm going to do is let's just ignore some parts of the diagram for now. So let's ignore all of this for now. And just focus, or let's do the other way around. Let's ignore all of the 25 condition for now and focus on the 29 condition. What does this 29 condition really mean? 20, 21, 29. You look back at our list here, 20, 20, 21, 29 is a Pythagorean triple. And if they're a Pythagorean triple, that means it's going to be a right triangle. So that means this angle is a 90-degree angle. That's interesting, isn't it? So not only is it true that a right triangle has sides that are Pythagorean triples, but Pythagorean triple sides, triangles that have those sides, are right triangles. And now let's add back this over here. And see, remember, this was 25. Now look at this. We'll erase 29 now so we can focus. Look here, 15, 20, 25. Now, this is not one of the Pythagorean triples we learned. But with some practice, you'll see that you'd always check if these sides will form a Pythagorean triple. And notice how they all share a factor of 5. So if we divide by 5, we have 3, 4, 5. Aha! We know 3, 4, 5 is a Pythagorean triple. And as we learned, if we multiply all the sides by 5, but they'll form another Pythagorean triple. Because it's the same ratio of sides, it's just scaled up. So that means 15, 20, 25 is also a Pythagorean triple. So we can put a right angle here. Whoops. We have a right angle right here. And that is right. Get it? So now, how do we find the area of the quadrilateral? So the key thing here to notice is these two angles are 90 degrees. And what we can actually do is extend both of these sides out a little bit, just so you can see. And let's fluff up this transversal here. And what I'm going to do is I'm going to draw an, oops, not like that. I'm going to draw a nice big line like that. These angles are both 90, and we've already used this condition, so let's erase it. These angles are both 90, so try to make an observation if you can here. These two angles are 90. This is kind of like a transversal, isn't it? Through two lines. What does that mean? If you want to think about this for yourself, you can pause the video. So what this actually means is that because this angle is 90, supplementary angles, this angle will be 90 as well. Okay, and because this angle over here is 90, this angle will also be 90, and that because of supplementary angles, and that means this angle is also 90 by supplementary angles. And that means this angle is equal to this angle. That's corresponding angles. Remember when parallel lines intersect, these angles are equal. In this case, those two angles are both 90. So these two, what does that mean? That means these two lines are parallel. And if those two lines are parallel, then we can use, what kind of quadrilateral is it then? It's a trapezoid because the two bases are parallel. So, and if two bases are parallel, this over here will be the height because it's 90 degrees to the base. The area of the trapezoid is height, half, times the average of the bases, times the height, which is 20. And half times 20 is 10. So this becomes 360. And that is the answer for this problem. Now let's explore this example, another one where we have to break quadrilaterals into triangles to solve the problem. ABCD is a rectangle with AB equals 10, BC is 12, and M, okay, let's draw everything out. AB 10, BC 12, M is the midpoint of CD. So notice because it's a rectangle, 10, 10. So therefore, this part must be 5, and this part must also be 5, because there's a midpoint. And we're given that P is a point such that BP equals BC. We know BC is 12, so BP must therefore also be 12. So this is nothing but 12. And rectangles, well, first of all, we know these are all going to be 90 degrees. So now this is a very complicated diagram, especially compared to the simple trapezoid. So try to zone in on a certain part of the diagram. Any specific observations, any conditions we know, anything. Just try to focus on something, maybe. Anything that seems familiar, pops out. The thing that popped out to me first was this 5 and this 12. We know 5, 12, 13 triangles. 5, 12, and conveniently they've even given us a right angle. 5, 12, 13. So we know therefore that this whole thing over here, let's draw it. Let's use this highlighter. BM will be 13. Not just BP, the whole thing BM is 13. By 5, 12, 13, right triangle. It's a Pythag triple. We learned that in the triangles class. So this whole thing is 13. BP is 12. So this extra part, PM, is just 13 minus 12, 1. Let's draw that in. So we've got this extra part, PM, over here, is just 1. That's it. What are we looking for? We're looking for the area of APBD. That is a quadrilateral indeed. Okay, but that's not a trapezoid, it's not a rhombus. We can't just apply our area formulas, can we? We're going to have to do something clever. And like I mentioned the idea earlier of breaking quadrilaterals into triangles. Notice here, APPD, this is the quadrilateral. We can break it down into two triangles, this one and this one. So let's find the area of each piece separately. First, the area of the orange part over here. The area of this orange part on the inside is just half times base, which is 12, times height, which is 60. 60. Now, the tricky part of this problem is figuring out the area of this part of this triangle. Right? That's not just a simple right triangle where we know the base and height. So how should we do that? So it seems like this purple triangle is almost this triangle here. It's so close to being there. So now this part has a very cool solution. It's almost like that triangle, except it's just maybe if we can find the area of this triangle and the area of this triangle, we can maybe subtract them to get the area of the purple triangle. We could do that maybe. Okay, so first things first. Let's find the area of this blue triangle I'm about to highlight. This one. What's the area of that triangle? Well, this is not like a regular right triangle, but don't be tricked by it. We still know the base and the height. The base is 5. This part over here is 5, and the height is 12, right? Because height is the one that forms 90-degree angles with it, not the whole segment here. So the height is 12 because it's the one that forms 90-degree angle with MD. So half base times height, that's 30. The area of that blue triangle is indeed 30. So how do we use this property maybe to find the area of the purple triangle? And this is where the property I mentioned in the triangles video of looking at the area in different ways, drawing heights, looking for common heights between different triangles. And if you remember from that other video, I'll quickly summarize that part here. We had an example where we essentially, if we had a height common, and this base was, let's say, B1, and this was B2, because they share a common height, they both have a height h. The ratio of the areas, this area to that area, was just B1 to B2 because the height was the same. So we're going to have to use that idea is very important. Let's see if we can use it here. The area of this thingy over here, we found to be 30. But we're trying to find the area of the purple part. But notice here, they actually both share the same height. Yes. So remember, height is 90-degree angle has to form. So this over here will be the height. Now the area of the blue triangle in terms of h is half times base. The base of the blue triangle is 13, remember? Remember, 12 was just this part, and 13 was the whole thing from here to here, all the way till M, from here to here. Because of 5, 12, 13, if you remember that. So half times the base, which is 13, times the height, which is h. That's the area of the light blue triangle, which we know to be 30. But we're looking for the area of the purple triangle, what is the area of the purple triangle in terms of h? Purple triangle area is half times base, and this time we know that, oops, that's not what I meant to do. We know the base of the purple part is 12, right? 12 is from BP. It's from B all the way till P. We know that's 12, and we know the height is h. So half times 12 times h. We know half times 13 times h. So to find half times 12 times h, we just take 12/13 of 30, which is 360 over 13. So we now know the area of the purple triangle. So what is the area of the quadrilateral? The sum of the areas of the blue piece, which was 60, sorry, not the blue piece, the orange piece, which was 60, plus the purple piece, which was 360 by 13. And now we just add fractions. This is 780 by 13 plus 360 by 13. And if we add this up, a quick way to do this is 780 is 800 minus 20. So 800 plus 360 minus 20, which is 1160 minus 20, 1140 over 13. And that's our answer. A great problem, isn't it? So the main ideas for this problem is to first, you notice that the 5, 12, 13, that was a key observation. I mean, 90-degree angle, always right triangles, look for Pythag triples, even if they don't give you a right angle. If they give you a right angle, even better. But even if they don't, keep an eye out for them. They're looking at you, and you should be looking at them too. So 5, 12, 13, we found BM. And then we noticed that, oh, right, we know BP is BC, so this part is also 12. And that means this part is 1. And from there, we realized APBD is nothing but two triangles, right? There's no formula for area of irregular quadrilaterals. So two triangles. The first part was pretty easy, half times 10 times 12. The second one was a little harder, but we use it using ingenuity. So basically what we had to do was realize that it's very close to being this big triangle, and that if you found the area of the big triangle to be 30, it has the same height as that blue triangle, the purple triangle. So we could just see that common height, the base is 12 to 13 ratio, and we found the area of the purple triangle, and then we just add them up. Key idea was always be on the lookout for the same height thing, where if we have two triangles, it's going to be a very common pattern where two triangles that share a common height. Be on the lookout for, you can easily find the ratio of areas by looking at the ratio of the bases. And that is really the main takeaway of this problem. And also, you should look at if they have the same base, and then obviously you can easily find the ratio of the areas as well by just looking at the ratios of heights. And you can find all these practice problems to practice your knowledge from this video in the free Mastering AMC 8 book. Link is in the description. For now, we're ready to move on to circles. Now we're getting a little curvy, but we're checking out some cool properties of circles right over there.